Hi, welcome back. Today we're talking about vectors. We're going to go through addition, subtraction, multiplying, and dividing. How to draw vectors, how to go tip to tail, and how to do the resultant when given two component vectors. Independence of dimensions says we must deal with the x and the y components separately. We've already talked about these two terms, vector and scalar, and the difference between the two is that the vector has direction where scalar is only a magnitude. Some examples of a vector are displacement, velocity, acceleration. Scalar, however, pressure, mass, distance, anything that's not directionally relevant. Vector addition. If I have two vectors that I wanted to add and come up with a resultant, let's call that vector C, what would I do? Well, graphically what we can do is we can take this vector and stick it on the end of this vector and then draw a line as a resultant. Now if this was on graph paper, I would be able to have the exact magnitude and direction assigned to these vectors, and this I could just read off from the graph and it would be accurate. So what we did was we connected the tip to tail of all of the vectors, maintaining their directions because the direction is important with the vector, and then we marked our start and finish time and then connected a line. Vector subtraction is very similar. The only thing you need to think about is adding a negative for subtraction, and we'll go through that with the math. Let's do an example. If I had vector A and vector B, well, A, B, start, finish, vector C. So mathematically, I had 4 plus 3, it's going to equal 7 meters for vector C. Vector A is all in the y dimension, and vector B is all in the x dimension. And so this is a good example of how you handle a vector that is in multiple dimensions, because the composite, or the I should say the resultant of A and B is going to be a oblique or an angle. It has some component in the x and some component in the y. And so what we are doing right now is we are going to handle the y dimension and the x dimension individually in order to find our resultant. Now this forms a right triangle because these are perfectly parallel with their respective dimensions. We still add vector A and vector B by putting the tips to the tails. We mark our start and finish and draw our resultant from the start to the finish. Now, what is the length of C? Well, being that this is a right triangle, we can use Pythagorean's theorem, where a squared plus b squared is equal to c squared. I want to solve for c, so I'll set this equal to c, and then I'll plug in my values. And I'll go ahead and solve. What I did was I added the y dimension component to the x dimension component to get a composite or a resultant vector that is in both the y and the x dimensions at the same time. Alright, so now I have an anti-parallel vector to the first one. So how do you deal with this? Well, it's the same way. My start to finish of my A vector, my start to finish of my B vector, and here's where the start and final finish is helpful because I know the direction of my C. Mathematically, you can think about this as adding the negative. So what this is vector subtraction in one dimension. And so I have A, which was 4 meters, plus B, which is 3 meters, but it's going opposite of my positive number, and so I'm going to put a negative sign on there, and that's going to equal my C vector. And so 4 plus negative 3, or in this case minus 3, right, ends up with 1 meter for vector C. Sometimes this will take the form of vector A is moving east and vector B is moving west, and so you would have to understand that you set north as a positive value and the east as a positive value, and so that would make west negative. So this will depend on your reference points. Multiplying and dividing vectors is pretty straightforward. Same direction as before, and so if I had a vector of A that was, let's say 3 meters, and I multiplied that by 2, then what I would have is it basically doubled in length. So now it's 6 meters. 3 times 2. Okay, the direction has not changed. The magnitude is the only thing that was adjusted. So dividing is the same as multiplying by the reciprocal. If I could take this same example where A is now 6 meters and I want to divide by 2, right? What I'm really doing is 6 times 1/2, or 6 divided by 2. Those are the same thing. And so if I divided 6 meters, the direction stays the same. I would just now be back to my original A equals 3 meters. If you are multiplying and dividing two vectors at the same time, so if you had an A and a B, so that two-dimensional problem we had, say these were airplanes. Airplane 1 was traveling this far at 100 miles per hour. Airplane B was traveling this way at 100 miles per hour. The resultant would be Pythagorean's theorem. But let's say that airplane A had some engine trouble and it had to cut speed by half. Well, now I have 50 miles per hour and 100 miles per hour, and so my C vector would change. Stays the same direction, it's just shortened, and I would deal with each dimension separately. That's it for vector addition, subtraction, multiplication, and division. Thank you.